This video discusses the reactions of ethers. Ethers are a fairly unreactive functional group. However, under strong acid conditions, these ethers can be cleaved to the corresponding alkyl halides and water. Generally, you need two equivalents of the acid. The functions of the acid are to protonate the ether oxygen to create a good leaving group, and usually the acids used will be HBr or HI, and this provides a conjugate base that is nucleophilic enough to do substitution to form the alkyl halides. If you have a weak nucleophile as a conjugate base, if it can function as a good base, it can sometimes do an elimination instead of a substitution. The mechanism of this reaction depends on the substitution of the ether. For methyl or primary ethers, the mechanism is an SN2 substitution. For secondary, tertiary, allylic, or benzylic ethers, which can form stabilized carbocations, the mechanism is an SN1 reaction. The first equivalent of HX makes the alcohol and alkyl halide. Depending on the structure of the ether, sometimes the reaction stops here with the alcohol and alkyl halide. The second equivalent of HX makes the second alkyl halide and water. The mechanism of this reaction will depend on the substitution of the carbon that's attached to the ether oxygen. So for instance, this is a primary carbon and this is a tertiary carbon, which means that the primary carbon is going to undergo an SN2 cleavage, whereas the tertiary carbon is going to go through the carbocation and an overall SN1 mechanism. We know that the products that are going to be formed are two alkyl halides and a molecule of water when we treat this ether with two equivalents of HI. So now let's work out the entire mechanism. Remember, the first step is to protonate the ether oxygen to create a good leaving group. So we start by drawing the ether. We have our strong acid, and the ether oxygen is going to deprotonate the acid. Now we've created a good leaving group, and we've also created a good nucleophile in the iodide anion. The iodide is now going to do a nucleophilic attack in an SN2 fashion. So this is an SN2 substitution, and we end up with an alcohol and our first equivalent of alkyl halide. So now you can see that we formed this product. For the second part of the mechanism, we're going to start with the alcohol that we formed. Remember, we already created the one equivalent of ethyl iodide, and now we need to cleave this carbon-oxygen bond. The first thing we're going to do is use our second equivalent of acid to protonate the oxygen and make a good leaving group. We've also, in this process, generated our good nucleophile, which is the iodide. Remember that this is a tertiary carbon, and so it cannot undergo an SN2 due to the steric hindrance, and it's going to form a carbocation instead and go through the SN1 reaction. So at this point, you've created the carbocation, you've also created water, and you also had iodide from the previous step. The iodide now attacks, and you form the final alkyl halide. And so you can see we'd already created ethyl iodide, now we've created tert-butyl iodide. So we've got this product, and we've also created a molecule of water. And so that completes the mechanism. Now let's look at this example. If we treated with two equivalents of HI and heat, what products would we get? Working out the mechanism, we know that the first step is going to be protonation of the ether oxygen with the strong acid to create a good leaving group. And so now we've created a good leaving group for our ether. And in the process, we've created iodide, which is a good nucleophile. This is a methyl carbon. It can undergo an SN2 reaction. And so we do an SN2 substitution to get to phenol and methyl iodide. Now with the second equivalent of HI, we would protonate this oxygen to make a good leaving group. However, because this is an sp2 hybridized carbon, we cannot do SN1 or SN2 on this carbon, and so the reaction is going to stop here, despite the fact that we have two equivalents of HI. And so our final products here are phenol and methyl iodide.